welcome back to Honors Biology. So today we're going to be talking about non-Mendelian genetics, and the next couple of videos are going to be about non-Mendelian genetics. So they're genes that don't obey Mendel's law of segregation, independent assortment, or the dominant and the recessiveness. So let's get right into it. So the first type that we got is just a reminder that there's two types of human chromosomes. So there's autosomal chromosomes. So remember, we have 23 different chromosomes. Each one has a pair. So chromosomes 1 through 22 are called autosomes. So everyone has, those same 22 chromosomes that code for the same genes. Yeah. So they're the same in everybody, regardless of gender. Up to this point, all we've been talking about have been autosomal chromosomes and autosomal genes on those chromosomes. The next are sex chromosomes. So those are chromosomes that contain genes that code for the sex of the individual, as well as there's other traits on the chromosome. Everyone has one copy. The 23rd chromosome is the sex chromosomes. Males are XY, females are XX. Physically, the X chromosome is going to have a couple hundred, if not a code for thousands of genes. The Y chromosome really only codes for about 70 genes. So the X chromosome has a lot more to it than the Y does. Now, that being said, there are some sex-linked traits, and these traits become more prevalent in men than in women. So there's disorders that are like hemophilia or color blindness. Hemophilia is the inability to clot. So if a person gets cut and they start to bleed, their body doesn't have the ability to stop bleeding. It doesn't have one of the factors that help stop it. And color blindness, with red-green colorblind being the most common. Even among genetic disorders, red-green colorblindness is the most common genetic disorder that affects primarily males. And the reason why is because males only have one X chromosome. Therefore, if that one X chromosome has the recessive version of hemophilia or colorblindness, they're going to have it. All right. They rarely show up in females because in females, both of the X chromosomes have to have the recessive version in order for it to be shown. All right. There are a couple Y-linked disorders, including male baldness and some forms of infertility among men, but there's not a whole lot found on the Y chromosome. And then females cannot have Y-linked disorders, so that's why females cannot have male pattern baldness, is because it's on the Y chromosome. So only men can get it. So let's just work through just some simple or some sex-linked Punnett squares problem. So it says hemophilia is a recessive trait linked to the XX chromosome. What are the genotypic-phenotypic ratios of a cross between a carrier female and a normal male? So sex-linked problems, we write them a little bit differently. First, how we do them is we just start by writing just the chromosomes of the male and the female. And now, traditionally, the male goes on top and the female goes on the side. But it doesn't matter to me which order you put these in. Okay, it doesn't matter to me. So here's that. And then it says normal male. So if the male's normal, that means the male does not have hemophilia. So we don't see hemophilia. So that means this X chromosome does not have the recessive trait for hemophilia. But it says the female is a carrier for it. So she carries the trait, but it's not shown. So that means one of these X's has the trait. So to show that, we superscript the H. So the H is superscript, so it's very tiny, it's above the next H, and then nothing on this chromosome. And now we just go ahead and we just fill it in. So we do X, H, X, X, X. And this is just bringing those, what's over here and what's up here, just across and down. X and Y. So what we got is whenever we deal with problems with sex-linked problems, we have to determine, what's the probability of getting a male or a boy or a girl. So male or female here is 50-50. So there's a 50-50 shot of this offspring being male or female. And then if it's a male, just looking at just these two boxes here, there's a 50-50 shot that the male will have color blindness. Or sorry, will have hemophilia. There's a 50-50 shot that the male will have hemophilia. With the female, there's a 0% shot that the female will have color blindness. Now, one of them may be a carrier, but neither of these females are gonna have hemophilia. One may be a carrier, but that's it. Let's work through another one. So another one says, red-green colorblindness is a recessive trait linked to the XX chromosome. A red-green colorblind female and a normal male have a child. What is the probability, regardless of gender, that it will be red-green colorblind? So we always start just by listing our chromosomes. So we have the X chromosome, the Y chromosome, X chromosome, X chromosome. So now based off of that, right, we got normal male. So the male is normal, so he's fine. We're not going to do anything to his chromosomes. But it says a red-green colorblind female. So since the female is colorblind, that means both of these X chromosomes have to have it. So I'm going to add just an R here. And now we just drag it. Now we just fill in our Punnett square. So X, R, X, X, R, Y, X, R, X, X, or Y. So now if we look at this, it says what is the probability, regardless of gender, that it will be red-green colorblind? Well, if we were to look, okay, the two boxes here, neither of these kids will be red-green colorblind. And that's just because for these to be red-green colorblind, both of the chromosomes are going to need to have the recessive trait. So both are going to have the little r. So neither of the females are going to be colorblind. But the males, both of the males are going to be colorblind. And that's because the mother, the female, can only give an X chromosome with the recessive trait on it. And because the father gives the Y chromosome, that means that then the female is going to give the recessive trait on the X chromosome. So if they have a male, if they have a boy, it's going to be red-green colorblind. So based off of that, just regardless of gender, that would be red-green colorblind. Well, I have two boxes here that are going to be red-green colorblind and two that are not. So overall, we have a 50% shot. Whoops, I don't know how that happened. But we have a 50% chance that the offspring will be red-green colorblind. So that's it for sex-linked traits. Let me know if you have any questions, and I'll see you later.